啊，那个，哦哦，他终于病倒了，终于病倒了。他还没有变好，还更严重。哦，没有讨论为什么那个 NBA 球员可以自控啊？为什么可以自控？自控停在哦哦哦，那球，到底什么？Spherical 还有一个东西啊，那个第三来之前那个最高。对，感觉上哦，他们停在空中会比较怎样找到那个 maximum？呃，跟好像跟核心力量有关系啊。罗浩想看，想 try。相公。哦，冲出去了，然后被拉黑了。对，二百 K，有被砍的，有那个有被那肯定有那个被偏向员工，这方面是吧？有，可以啊，那个我觉得可以，不投了，投了，差不多概念，就一个是在地球，一个在地球外面了。干嘛？这个给了，那可以，不一样就是可以的。它是引力，不是？像引力把它甩出去那个，对啊，投篮是人投出来的。那个投射因为我要距离啊，然后那个高那个跑线、风向，行吧？那现在就这样子。 Hello, testing. Okay, good afternoon to everyone. For those who sent me your draft, I will hopefully will get you back this weekend, by this weekend. And for those who haven't decided your topic, please decide it soon. This weekend as well, because you need another week to prepare your slide. So I put out the lecture note for last lecture, and I included the working from Chenjak. You will have a look. Of the volume of this paraboloid. What if you parameterize the circle using the xy coordinate, which is the rectangular coordinate? How do you find the volume, right? And you can see that you need to go through a lot of integration on square root. Well, how do you do it? You exactly do it using the Spherical substitution. And then actually we start with a polar coordinate, which is also trivial. So we pass by these step here. So that's why in calculus 1, when you do integration on square root stuff, you will have to do trivial substitution. It's exactly because you are transforming the variable to polar coordinate. Okay. So now you should have a better idea what the polar coordinate is. And then this question here satisfies the symmetry, okay, symmetry, rotational symmetry. So you can just integrate along one quadrant here, pi over 4, right? So you could see that there's really nothing depending about theta here. So if you reduce this domain to pi over 4, you exactly get pi over 8. Okay, and then multiply by 4, you get a whole volume here. Okay, now. I want to go through the last example we finished last time again. Okay, so last time we talked about finding the hypervolume, okay, or the triple integral of this function z. Okay, this function z on above, or not above, but the domain over the domain, which is a solid tetrahedron here. What's the hypervolume of z? Okay, and last time we decided to do dx, dy, dz. Okay, so meaning we fix from the outermost variable. Okay, so we need to fix from z, and then fix y, and then fix x. Okay, still remember? Okay, so when we fix z, where's the domain here? So we're fixing from 0 to 1. Okay, so you're starting from this line here, 0 to 1. And then you look at what happened to y. So meaning you look at the zy plane, okay, or the x equal to 0 plane, right? So you get this triangle at the side here. Okay, so I move it down here. So you should think of it, you start from a line. Okay, how to make a triangle? So on each line, you have to add a different length of line, right? So you can map out this triangle here. Next, we need to determine what happened to the x direction. Okay, so meaning for all the point on zy, you need to attach another line again, all the line to make up the solid tetrahedron. Okay, so this is how the how you bisect. Okay, bisect is not bisect. What do you do to a mouse? Dissect. Dissect, right? Okay, this is how you dissect the tetrahedron here. Okay, you start with a line. Okay, and then you add up a bunch of line in different lengths. Okay, so to make up this triangle here, and then from this triangle here, you attach a lot of line again.
okay, to fill up the solid tetrahedron here. Can everyone get this tetrahedron shape here? Okay, everyone got it? Can you imagine? So we start with the backbone. Right, we start with the bond. Okay, I put flash on the triangle side, triangle base. Okay, and then I fill up the tetrahedron. For each point, I have a line. Right, is it a line here? Because x is bounded below by 0, bounded above by 1 minus z minus 1. So this is an interval. So on every zy, you have an interval on x. Make sense or not? Does it make sense? So let me repeat again. So you start with an interval, correct? Not 0 from 1 is the interval. Okay. How about y direction? So on every z, you have different interval. Okay, on every z. So imagine this is your z. Okay, and on every z, you have different interval attached. Okay, and then you make out this triangle here. And then from every point in this zy here, you attach another interval, the third interval. So you attach all the interval here. Okay, to fill up the solid tetrahedron. Does it make sense or not? You know how we dissect the shape? Right, we start with a line, and then we attach line on the lines, and then we attach line on the area. Okay, to fill out the shape. Does it make sense? Make sense or not? You can think of a mesh. You know what's a mesh? Is it called a mesh? What's higher? Mesh, right? Okay. So you take a mesh, okay, and then you take different length of mesh attached on it. And you take one mesh here, and then take different mesh attached on it. Okay. So you fill the area. How to fill the volume? You take more meshes, okay, to fill up the volume here. Make sense? Make sense? Okay, we try another direction. How about dy, dx, dz? Okay, so meaning we need to fix from the outermost variable. We fix z first, and then we fix y, fix x, and then we fix y. So we start with the line interval, okay, from 0 to 1 for z, okay. So this is the 0 to 1 line. And then we look at the zx plane, okay, we look at what happened to the x direction. So similarly, on each z, I attach different length of meshes, okay, depend on my z here. Okay, so I got a bunch of line interval here. Right, this is the line interval. Agree? Okay. Because there's another notation I can write here. So I can write it like this. So Z. So there's another notation I can write here. So I can write Z is in the closed interval from 0 to 1. It's an interval. Okay. And then X is also in the interval. So this X here has different interval depend on your Z. Okay, how is it depending on Z? When Z equals to 1, it is just 0 to 0. When Z equals to 0, it is 0 to 1. Okay, so on. So you back out all the length here. Okay. And then how to fill up the tetrahedron? You need meshes on the other direction. Okay, to fill everything in the base, right? So your Y is in from 0 to 1 minus Z minus X. So meaning what? The length of the meshes you add in is depending where you add the ZX plane. Correct or not? Right. You can see that at this point here, you have length 1. Okay, but at the point Z equals to X equals to 1, Z equals 0, you just get, what do you get? You just get 0. Okay, and then you add a different length of meshes. Then you can fill out your solid tetrahedron here. Does it make sense? Make sense or not? Any question seeing this. You can see that these are the two ways you dissect the tetrahedron. Can you see? The first way we build from the ZY direction. The second way we build from the ZX direction. So one is coming forward, one is coming going to the right. This one is coming forward, right? And then this one is going to the right. Does it make sense? Sense or no? Don't be afraid to ask. You should try different way. Okay, please try in different way. So you have 6 ways. There are 4 more ways here. Could you draw this shape or not? Do you know how you build out the tetrahedron using different order? Please draw it out. Okay, if you draw it out, you can send it to me, and I can have a look. Please try. Try and draw the other 4 order. Okay, see how you dissect your tetrahedron. Okay. Okay, I'm trying to draw it. Okay. So how? Okay. So right. Okay. Let me just stop here. Okay. Any question that you want to follow up here or no? Okay. If not, let's continue. Let's introduce the triple integral in different coordinates first, and then we will do more exercises. Okay. So let's look at this spherical coordinate. Okay. So last time we started with triple integral in the rectangular coordinate. Okay. So you use boxes to fill up your space. Okay. But similarly, we can fill with sphere. Sphere, like a ball, a hollow ball. Okay, you imagine the basketball, right? Inside is hollow. So you imagine a ball. Okay, you can feel, you can take any point in the space. Okay, and then this point will stand on one of the ball. Okay, centered at the origin with certain radius. Okay, so how do we do this? So we take any point on my space, right? Call it P, X, Y, Z. How do I find the sphere that contain this point, right? So how do I find it? Any idea? So I need to find a sphere, right, that contain this point. Okay. Yeah. Any idea how to find the sphere here? Huh? Find the radius first. Okay, similar to the what's the case? The R2 case, right? In the polar coordinate, you find the distance between the point to the origin. Okay, and then from there you can draw a sphere with that radius. Okay, so how to do that? So since you have x, y, z, right? So how do you find the distance between the point x, y, z and the origin? Equals to. Okay, so you take square root of plus y squared plus z squared. Okay, so this is the radius. So you get the first equality here. Right? Radius square equals to x squared plus x squared plus y squared plus x squared. Okay. So how do you parameterize point on the sphere? Okay. So how do you parameterize it? It is actually given by this top tree here. Okay. So we are parameterizing points on sphere using radius, phi, and theta. Okay, so you know about phi. So what is this phi and theta here? Okay, what's phi and theta here? Right. So theta. So where is theta? So theta is here. Okay, so theta is the angle you make on the xy plane. Okay, so your angle from the positive x-axis on the xy plane. Okay, so this theta here is similar to the R2 case. Okay, so you use theta to swipe out a circle on the xy plane, right? And then you can use radius to increase or decrease this circle here. But this only span R2, right? You only can get R2. How do you get all the other points in the space? Okay, you need another angle. Okay, you need to bring your vector away from your xy plane, and then that angle is what we call the phi. Okay, this is the angle we call phi. What is phi? So phi is the angle you make from the positive z-axis. Okay, so you need an angle to bring up your vector away from xy plane, so that you can cover everything in the R3, right? So to cover, right? Can you tell me what's the domain? What is the interval we should take for rho, phi, and theta? Right? For rho, theta, phi. Okay. What's the domain where these values lie, so that you can cover the whole R3? So what radius? Okay, maybe tell me what's the theta you should get. 0 to 2 pi. Okay, you swipe up if you take 0 to 2 pi, you swipe up a circle, right? And then less than infinity, right? Okay, so with rho and theta, you will swipe out the whole R2. Then how you swipe out the R3? P have to take from where to where? Negative pi over 2 to pi over 2. What is negative pi over 2 to pi over 2? Right. So, but my direction is going from positive z-axis, right? So here is 0. So if I go downward, or if I go down this way, pi over 2 is here, right? Where's negative pi over 2? It's on the other side. So you kind of swipe out from here to here. Let me think. So on this side here is 0 to pi over 2, right? This orientation is a bit weird. Let me think, where's the orientation? So I count my phi. Where do I count my phi? I count my phi from the positive z-axis, right? So I'm going this way. So phi going from z, going down. Okay, pi over 2 is here. Where's negative pi over 2? Negative pi over 2 is. Then let me think. Okay, I think I know where's your orientation. Your orientation is here. So here is pi over 2. Here is negative pi over 2. Negative pi over 2 to pi over 2. So it should be like this. Orientation like this. Okay. But the convention way is to take 0 to pi over 2. 0 to pi, sorry. 0 to pi, correct. Yeah, 0 to pi. So these two will give you the R3, but they sum up differently. I mean, you describe your point differently. Okay or not? Is it okay? Does it make sense or not? Why I just need half of it? Why do I just need half of it? Is enough. Huh? Once. Oh. So you have half of it, right? Okay. But remember that your theta can go from 0 to 2 pi. Okay, so this means this half piece here, or the half watermelon slice, if you want to think about it, you can swipe across the whole arch. Does it make sense or not? Okay, you should imagine, okay, let's draw it properly here so that you know what I'm talking about. So here is that, okay, and then we draw a x, draw a y here, and then draw an x here. Okay, so if we just have phi, okay, if we just have phi from 0 to pi, okay, so you can think of this as a slice of watermelon. Okay, that's a slice of watermelon here. Okay, but remember that your theta, your xy plane angle, you can swipe from 0 to 2 pi. In that case, you swipe the whole sphere. Does that make sense? And then once you swipe a whole sphere, just now we say that this radius is greater or equal to 0 or less than infinity. So you can increase the sphere to fill out the whole space. Can you imagine what am I talking about? Imagine or not? Are you following? Answer. Okay, I repeat again. So wait, let's hold Zhengkan domain first. Okay, let's take. Okay, so let's take 1, 2, 3 first. Okay, so if I pick phi from 0 to pi, what does it mean? I have the angle all the way from positive z-axis to negative z-axis, right? So you think of, you take a vector, okay, from 0, from the positive x-axis, swipe out the, swipe out what? A half circle, half this to the negative x-axis, negative z-axis, okay? And then what's the variable for theta, for example, right? Theta is the angle on the xy plane, right? Xy plane. So you can take this, okay, and then do theta from 0 to 2 pi. Does it make sense? You take this slice here, and then you do 0 to 2 pi. What did you swipe out? You swipe out a sphere. Correct. Okay, imagine this thing is a half this, okay, not rectangle. Okay. Then if you swipe across 0 to 2 pi, then you will form a sphere. Correct. Okay. And then what's your radius of the sphere? It could be 0 all the way going to infinity. So you can think of this sphere is increasing. Then you can fill out the whole space in R3. Does it make sense? Make sense or not? Okay. Yeah. Yeah, 5 feet. Sorry? We haven't discussed this yet. Later we'll discuss this whether this will or not. Let's take this. Let's take my choice first. Yeah. Okay, no? Okay, okay. How about take this Zhengtan choice here? Okay, Zhengtan choice here is referred to where? Look at this cross here. It is going from negative pi over 2 to pi over 2, right? So is it this way? Let me think. Okay, let's say start from z axis. So let's say, okay, maybe let's say take this. Let's say take this domain here. Is it possible to generate R3 or not? Yeah, is it possible to generate R3 if I take this? No, right? So I just take the watermelon slice and then I rotate it. I only get a half sphere. Okay, I only take a half sphere. And then I increase in radius. Wait. Okay, so wait, let me see. Okay, so yeah, so it's like this, right? So let's say you are considering minus pi over 2 to pi over 2, right? You only like this. Also, okay, I mean, yeah, maybe this one you look a bit more like a sphere here, right? So you only have this, correct? No, from minus pi over 2 to pi over 2. Does that make sense? So how should we imagine this? You should imagine there's a vector, right? This vector here can go from minus pi over 2 to pi over 2, a fixed vector. And then this will swipe out the watermelon slice here. Okay, and then your angle theta is going from 0 to 2 pi on the xy plane. So meaning you rotate this watermelon slice here. So what do you get? You only get half of the sphere, which is a semisphere. Okay, and then your radius is going from 0 to infinity. So you only cover half of the R3. Okay, to cover the other half, what can you do? One way you can do is you increase your radius to the negative way. So instead of starting from 0 radius, you can start from negative. Okay, bounded by negative. So you can reflect the radius the other way. Remember this property in your polar. Okay, yeah. So depend on what interval you take, you might consider a different domain. Okay, does it make sense? Make sense or not? Other got question? Got question? Okay, so if you consider different domain here, okay, maybe you need to consider a different set of variable, right? Different set. Your variable live in a different set. Okay, so then you will get the same space. Does it make sense? Okay. Okay. But in general, so what's the formula here? Okay, so this formula looks a little bit complicated. So x is equals to rho sine phi cos theta, y equals to phi sine phi, rho sine phi sine theta, and then z equals to rho cos theta. Actually, you can check that this satisfies some projection onto the xy plane. Okay. If you disregard this phi here, right? If you disregard how high is it, okay? Rho cos theta, rho sin theta is exactly the polar coordinate, okay? Why there's an extra sin theta here? Because you have another circle that is orthogonal to your circle in the XY plane. Okay, does it make sense or not? This is another way to see a sphere. How to see a sphere? You have a circle, right? And then you can have another circle sitting on it. So let me draw it for you. In this course, are very important to slice or dissect this shape differently. Okay, so how to imagine a sphere? There are few ways to see this sphere. Okay, you can take a circle to build this sphere. How to build? You just take a circle, right? And then you do rotation, right? So what do I mean by doing rotation? You fix this two sides here, and then you turn it around, right? You turn it around. Okay, no? You fix a circle, and then you hold the two sides, and then you turn it around. So make these two a fixed point. Okay. The other way is you can take the horizontal. Maybe draw like this. You can take this horizontal circle here. Actually, we call this a great circle. So you can take this horizontal circle here, and then you can consider another circle like this. Another great circle here. Okay, and then you fill up the space between these two circles. Right? You know what I mean by fill up the space? So if you take two circles, right, you put like that, you should have 4 surface to fill in. And imagine or not? Okay, so these two circles here, right? These two circles here is exactly what give you this cos theta, sin theta, and sin phi and cos phi. Okay, so theta referring to the horizontal circle, and then phi referring to the vertical circle, which was sense or not? Okay. Okay. Yeah. So think of this way. So think of this way. Think of this. Think of this. So how do you make up a sphere? Right? How do you make up a sphere? How do you make this sphere here? You really start from the circle, okay? And then try and leave this. Leave, for example, okay. This is the origin, okay? So how to make a circle? Yeah. How to make a sphere? You take the point or the vector that point to the circle, and then you slowly leave the vector out. Then you swipe out a circle, okay? And similarly bring it down. Okay, so this is what the spherical coordinate do for you. Okay, you take the point on the circle, and then you slowly bring it out using the phi angle. Okay, make sense or not? Does it make sense? Okay. It's very important to have different way to think about this sphere so that you can appreciate this change of variable more. Okay, it's not just phi times sine, phi times cos theta. Okay, some weird combination. Okay, it's not weird. Okay, it's basic, based on how we dissect the sphere. Does it make sense? Make sense or not? Try and think about it. Okay, how to think about a sphere. How you make the sphere. Okay, how to make a sphere. Okay, can. So let's try this. Okay. Should we do one more exercise to convince us this variable is making sense? Can we all check what is x squared plus y squared plus z squared? Let's do this. Let's verify this. do we really get rho square or not? Okay, yeah, let's try and do this. Try and expand this. What is x squared plus y squared plus z squared in terms of rho, phi, and theta? Why does phi and theta disappear? Yeah. Let's try it. So what is x squared plus y squared plus z squared? Okay, anyone finish or not? Okay, so you can see that few terms appear in more than one term, right? So which one you can simplify first? The first two can be simplified first. So you can simplify the cos square and sin square, correct? But cos square plus sin square is just 1, right? So again, you simplify the sin square phi and cos square phi, which also simplify to rho square. Okay, so did you notice why here two of them got 2 angles, but one of them only got 1 angle? So from the discussion just now, right? So these x, y, right? So they are lying on 2 circles. So you have a horizontal circle and a vertical circle. Okay. But on the z, the horizontal circle is always 0. Okay, so that's why you don't need to care about the other angle there. Okay. So this is another reasoning how you remember this equation here. So I have finished preparing the test. So for your test, right, there won't be practice exam question because in the final you can't bring your cheat sheet. I'll prepare the definition and theorem sheet, and then I will release soon, okay, to you to prepare. I mean, practice question using those definition and theorem. Other than that, I won't provide other theorems or definitions. And the question is quite, they're not quite hard. I mean, there are true or false question, of course, concept question, but the calculation question will be mostly like the review exercise I gave in the Moodle. Every chapter I gave review question, right? So please make sure you practice them, okay? And then also the tutorial question, of course. So those are the typical exam question you will see for the calculation. Okay? And then, yeah. And then I will also release some quiz question that we used last time, and you also can practice using that. Okay? So there will be no past year exam question for you to practice, but you should practice using the review questions. Okay? And then I will release a quiz for you to do also. It's not for your assessment. It's just for you to practice. Okay, but it's coming from the other class last time, which is useful. Okay, so let's do one change of variable exercise here. So let's find the rectangular coordinate of the points whose spherical coordinate are just 2 pi over 4 and pi over 3 here. So there are two angles here. So you need to make sure which one is theta, which one is phi. Okay. So which one is theta, which one is phi? Let me see. What's our convention here? Okay, so let's fix the convention in this class. So which convention we are using? So we will be using B and then theta and phi. Sorry, rho, theta, and phi. Okay, this is the convention we use. So we fix radius first, and then we fix the xy, the angle in the xy plane, and then we fix the angle in the z direction. Okay, so this is the convention we use here. Because there are two angles inside your expression, so maybe you were confused. Okay, let's fix this convention. So we will find what is x, what is y, and what is z. Okay, so what is x? Right? Square root 2 over 2. Wow, so quick. What's the formula you use? Yeah, so what is it? Rho sine theta sine phi cos theta, right? So what is 2 times the sine of pi over 3 times cos of pi over 4? Is this square root 2 over, what did you say just now? Square root 2 over 2? Okay, please compute. Is this square root 2 over 2? Huh? Right? Is this, because I have a different answer here. Is this square root 2 over 2? Please check. No? What do you get? Yeah, this sounds more like it. Square root 6 over 2. Everyone please compute. Is it square root 6 over 2? And your solution, you shouldn't leave your solution in decimal. Okay, the practice in mathematics is to leave it in radian. Okay, radian. Because decimal doesn't really make sense to maths because sometimes the decimal doesn't end. Okay, we like exact solution. Okay, exact solution. Radian, huh? Sorry, I mean in exact form. In radian, maybe you need to change to decimal again. Okay, in exact form. In the unit of pi or something like that. I mean for angle. If for angle you leave it in terms of pi. If for the other numerical solution, you leave it in the exact solution, like fraction, right? Don't make it into decimal. We like exact. Okay, how about y? Y is 2 times pi over 3 times sine pi over 4. Okay, so what do you get? Same, square root 6 over 2. Okay, how about z? 2 cos pi over 3, which is 1. Okay, so you have your spherical coordinate changed to a rectangular coordinate, which is square root 6 over 2, square root 6 over 2, and 1. See, the direction is correct or not? Positive x, positive y, positive z. So this is living in the right quadrant here. Okay, so when you after calculate, right, please check out whether your answer makes sense or not. Okay, if it doesn't make sense, then something wrong in your calculation. Okay. Okay, maybe let's do one more exercise and then we'll take a break. Find the spherical coordinates of the point whose rectangular coordinate is this. So now we're going from rectangular to spherical. Okay, how to go? So you given x, y, z, how to find rho, theta, and phi. What equation you know? Okay, so you know all the how you write x, y, z in terms of rho, sine, and rho, theta, and phi, right? Okay, so you can form three equation here. Okay, let's form three equation here. Then let's form three equation here. So first equation you get is 0 equals to rho sine phi cos theta. Y 2 square root 3 equals to rho sine phi sine theta. And then minus 2 equals to rho cos theta. Okay, so how to reduce these? Sine phi. Use this. Then theta. You want to divide, is it? So let's put 1, 2, 3 here. You have to do 2 over 1. 2 over 1. That one should be infinity, the infinity. A bit dangerous. Okay, 1 over 2 also cotangent. If you want to solve cotangent, isn't it? Okay, I mean, yeah, make more sense, but similar. Cotangent 0 is also tangent infinity, right? I guess. Sine phi is minus 1. Okay, sure. I mean, how to say? You mean you want to guess from the third one, is it? But phi is bounded above by 1, bounded below by -1, right? You can't assume I always get 1 here. Correct. But what you can do is this one. Can you do this or not? Yeah, rho cannot be 0. Because if rho is 0, then the only point that rho is 0 is 0, 0, 0. You are not getting that. Okay, so rho is some negative, some non-zero thing. So if this expression here have to be 0, then either of the two trigo have to be 0. Okay, so from here, you should guess. Rho cannot be 0. Phi have to be what? 0 or pi. Alright, okay. How about theta? Power 2 or 3 pi over 2. Okay. Why we only pick these? Remember how we pick the region of phi and theta. Okay, where the domain, where they lies it. Okay. Wait, what are you doing? What are you trying to do? So you are trying to fix which one is which, is it? So which angle here represents this? Where does this point live? Where does this point live? Which quadrant? So not quadrant anymore. In R3, we call it a octant. What is an octant? You have 8 parts, right? Or you have 8 parts. How you imagine this 8 part here? So you got this slice and then this slice here. And then This only have 4, right? So you have another one in the middle. Okay, so you have 8 octane. So which octane this lies in? So where is it? Positive X, so 0, X, okay, and then positive Y, negative Z, okay, so going down. Okay, okay. Right. So let me use another color. Okay. So which angle fit this point? Which phi? Yeah, let me see. Is this the correct thing to do? Okay, so I think I less accurate here. Should be 0, and then 2 minus 3 xy, and correct, right? Yeah. Here is minus 2. Here is 2 square root 3. Okay, live in the zy plane. Okay, living in the zy plane. Okay, no, living in the zy plane. Okay. Okay, so which angle fit here? Hmm. You can find the radius first, right? We can find radius first, right? Okay, so what's the radius actually? Not just we know that it's non-zero, we actually know what is the radius. Radius square equals to, yeah, so here's 2 square, and then plus minus 2 square, plus another one is a 0 square. It's 4. Is it 4? 6, 4 times 12 plus 4, correct? Yeah, 16. So rho equals to plus minus 4, but radius is positive, so it is 4. So the radius is 4. Okay, and then we can plug this rho into 4 into 2 and 3. So what do we get? Sine phi sine theta equals to 2 square root 3 over 4. But cosine phi is very clear already, which is minus 2 over 4, which is minus half. So which phi give you minus half? Pi over 2 or 3 pi over 2? 2 pi over 3. Wait. So wait, let me see. So I copy wrong thing here. So theta, there's only 2 choice here, right? Pi over 2 or 3 pi over 2. Yeah. So which one fit into cos theta equals to minus half? Is it theta or not? Oh, phi, sorry, it's phi. Phi should be. Wait, what am I doing? Let me see. Phi. Wait, back calculation. Three. Wait, so here is 2 pi over 3. But why there's no 2 pi over 3 here? They don't always be both be 0, correct? Yeah, you're correct. Okay. Like here, let me make a note here. So make a note here. So one of these must be true for 1 to hold. Okay, one of these must be true. Okay, but just now we found that phi is not 0, is not pi either. Okay, so theta must become from one of these answers. Okay, so let's determine this. Let's continue. So since we thought we solve this first, let's put it here. Okay, then we sub this into here. So what is sine 2 pi over 3? What is sine 2 pi over 3? Negative 1, ah? Sure? You sure? So I get minus spherical. Huh? Huh? Positive or negative? Okay, let us draw the shape. Okay, so pi like this. Okay, and then here is 2 pi, here is pi. Yeah, this is wait, what is it? No, no, right? Wait, so here is pi over 2, here is 3 pi over 2. This is 2 pi over 3. So what is sine 2 pi over 3? Hmm? Did I do something wrong here? No, right? So what is sine 2 pi over 3? Negative square root 3 over 2. What? Huh? What? Wait. Wait, one by one. So what is sine 2 pi over 3? Square root over 2, ah? Okay, but others, please check, ah. So here I also got square root over 2, so cancel. I get sine theta equals to 1. But our choice is theta equals to pi over 2 or 3 pi over 2. So it must be pi over 2. That must be pi over 2. Okay. Yeah. High school math, need to pick up again. So this point here, 0 minus 2 square root 3 minus 2 get changed to 4 pi over 2 or 2 pi over 3. Okay. Okay. Yeah. Check first. Okay, I'm done. Yeah. Okay, before we take a break, let's finish up how good is this spherical coordinate. So for spherical coordinate, you can draw a sphere. So how to draw a sphere? Okay, you just take a constant radius function. Okay, you just fix the radius to some number, then you will swipe out the sphere. And surprisingly, this spherical coordinate can build a plane for you, a half plane. Okay, how to build a half plane? I just tell you what is the theta. Okay, I just tell you one direction, and then all the radius I want, all the phi I want. Okay, then I will build out the half plane. Okay, make sense? Okay, so if I fix theta, I get a half plane. And if I fix phi, what do I get? If I fit phi, okay, if I fit phi 0 to 2 pi 1, I need all the radius. Okay, I need all the radius. So either you are going all the way up or you are going all the way down. Based on what radius we have now. Yeah, no. So if you include your radius from negative infinity to infinity, you will get the 2 con. Okay. Yeah. If you get these 2 con, right, this is the con that I consider in the relativity. Yeah. The time con. Okay, no? Yeah, this course is very related to string theory because relativity, string theory, it uses vector calculus. Why vector calculus? Because you are dealing in R and n greater than 1 or R4. Then if got chance, maybe we can talk more about the relation. Quantum, not quantum physics, but physics with. Okay. Okay, let's take a break until 2:14. Project
我比较怎样可以让汽车飞最省油？首先是这样，我就想汽车开的时候它会做功嘛，发动机吃油，然后做功，然后就做功是这些，总共首先 PT 就是汽车往前走的那个力，然后 FS 就是摩擦力，包括地面摩擦。
P 是什么 momentum？P
是这个发动机的功率啊，然后就跟发动机，比如说 B4，
英语什么？英语什么？然后功率什么 ？Power 是吗
？Sometimes power 呀。
Power 乘 T 你会拿到什么东西 ？Energy 啊
？Yeah, energy。
OK，energy 呀 OK。呀，对 energy，因为这是
W，
这是 kinetic energy 是吗？
这个就是 work，就是做的所有的 work。FS 就是这个是摩擦嘛 ，F 是摩擦了
，friction。Yeah
friction。
S 是什么 ？displacement。
你说 S 吗？
对
，S
displacement 多了多远 ？OK， 对，没有错。
然后 mu S V 方 V 是 speed 啦 ，S 是 distance，mu 是一个 constant 啊，就是这个风阻系数。
所以这一个是空气的，就是地板的。
对。然后 mu 跟汽车的 shape 啊，材料很有关，所以也是个 constant 啊。然后所以耗油量就应该是它做的功，然后再乘上一个转换的数字啊。这个是我查的，肯定不会错了。
对啊。
然后转换系数，
你可以给一些 reference 在里面。
我会，但就很零碎，但是可能不精准，但是大概是这样子。
精准什么意思？
就是它可能，比如说它做工不只是，
可能它加了很多东西，
但是应该是空层了，后面就应该是空层。
不用紧，就是说，
就是影响到结果的，因为我是要算速度跟耗油的关系，就是什么速度最省油。
OK，
所以主要是 focus on V 啦。然后这个是转换系数，是个空层。这个叫什么 lambda。OK， 这个东西乘上这一串，就是我们要求的耗油量。因为我们是要求它最省油嘛，所以应该是在一个固定的。
这个 constant 是什么 unit？所以这个是
这个是它 energy， 这是所有的 energy 啊。
对啊，这是 energy 乘上
是耗油量，就是类似于
这个耗油量的 unit 是什么
？unit
量啊 amount。什么是 PC？PC
只是一个我看到
它叫什么 P？它叫它的名字
I don't know。
所以一个东西乘上 energy 等于耗油量。所以
就类似于比如说，
也是说你用了多少 joule，然后它就耗了多少油这样。
Yeah，
这个 constant。
也差不多。比如说你走5公里需要耗1个油，那这个就是那个
就是 liter per joule 这样。
现在就是 drops 吗？work 的单位是什么
？energy 不是用 joule？
J 呀，我跟你说 drop。我物理已经快忘记了。
OK， 然后
我们是要它最省油，就是单位距离。比如说 distance 是1个 unit 的情况下，所以应该 PC， 然后这是个角标了。
角标是什么？
就是代表它跟它有区别。
什么区别？为什么？
这个是单位距离，这个是总距离。就是
你是说 XY direction 啊？
这是一个
unit。OK，
所以应该是这是耗油量嘛？我们要求单位距离的耗油量，就应该这个东西再除一个 S。S
是什么？
distance。
OK，
所以这个东西就是
OK， 你要 per distance。
比如说他走了1个公里，他就耗这么多油。
明白。
所以这里空层就有 P、F，然后 mu，还有这个转换系数，然后会变的话就有 T、S 还有 V 方，然后我就算这样子，然后就求导反正什么事情不会就求导了，求了以后就变成这样子。
对着什么球？speed 球。
对着 speed 球。
然后其他的 variable 不会 depend on speed 吗？friction 不会 depend on speed，因为你越冲越快的时候。我会把 speed 除进来嘛。S displacement 嘛。distance 也对，差不多。 distance 对。
然后所以
T 除以 S 就
我是说
等于
friction 会不会 depend on V？
不会。
为什么？
friction 是
摩擦力。
摩擦力，静摩擦。这个平放在这里，不管它速度多快，它的摩擦力是固定的，对吧？我踹它一脚，它往前走，它一直减速。Like what？我们画个受力摩擦嘛。这个是汽车了。它受一个重力嘛。G F。好，它受到一个 F 等于 μ G F。F 等于 μ G， 只跟 μ 和 G 有关，μ 是地面的摩擦系数咯。G 是重力。
OK。
然后TCR 等于这三东西。这个跟 V 没有关系，这两个都跟 V 有关系，所以进行一个dV 以后，它就这个东西就没了。变成这样子。
OK。
然后就得到一个结论，就是有没有比？speed，这是 speed，然后是它的单位距离耗油量，就是那个 TCR，它越小，它就越省油，就得到一个大概这样子。
OK， 所以 optimal 的 speed 是什么？
然后再算一次求导，因为现在只能得到速度很小的时候，它加速会省油；速度很大的时候，它减速会省油。所以现在就要求这个地方，所以就再求一次导，求2次导以后就变成这样子。然后就发现它是一个单调递增的，这个东西应该是一个一直往上走的。也就是说，它的1次导应该就是不是这个东西是个正数，所以1次导就应该一直往上走。所以我们只要找到1次导等于0的地方就好了。就是这一串东西等于0的时候，我们算到 V 等于 T 除以2μ。
等下你这个图是 differentiate 过后的这个图吗？还是
这个图啊，这个图主要讲的是耗油量，是 P。
这个图是这个图？
对，是这个图。
OK。
所以我们就知道这个地方，就最小的这个地方应该是 V 等于 T 除以2μ的1/3。
没有啊，这个，等下，这个图是这个图嘛，对不对？像这个 maximum minimum point 没有讲什么，没有讲东西是吗？
maximum 有啊，
就是说这个耗油量是最低的，在这里耗油量是最低，是吗？
对。
然后你现在要拿的 result 是什么？
然后我现在拿到 result 就算到这个点，这个点是什么？就这个点的速度是什么？
没有，这个 graph 是什么？
这个是耗油量，这个是 speed， 就是它的 speed 增加，它的耗油量会逐渐减小，但到了一定速度，你速度再快，它的耗油量也会增加了。所以我们要找到一个耗油量最小的地方，而这个地方就是1次导等于0的时候嘛。
OK。
对
，OK。
然后我们要求这个1次导等于0，就要增加它的2次导。
OK。
OK。
Yes。OK，就这样。OK。但是你这个球1次导有没有办法把这个变偏导？
偏导是什么东西
？partial differentiation， partial differentiation， 能不能再加一个因素进来？
我不是很记得名字。对的。
这个
这个没有谁。
对哦。你的笔那里这样跑在哪？有没有可能再加多一些因素进来？
那会变得很复杂。
一个加一个就好。
My purpose is to make audience all clear
没有，因为你这个只是 first derivative 嘛。我们学的是这个嘛。有没有可能再加一个因素进来？
但是因为我的 topic 是耗油量跟 speed 的关系，对我的。那如果要加一个变成耗油量跟速度还有汽车造型的关系，或这样子
也可以哦。那它体积也是吗？
这样你会给我更高的分数吗？
当然了。
All right, all 30 for you, boss
因为你这个差不多就是这样了嘛，对不对？
Yeah.
对，能不能再加多一个 variable 进来
？OK，
这样就是考科2了。
You're right. Next time, buy car, ask me for advice. I'll choose one very safe oil for you.
比如你的那个 constant 里面，玩你的 constant。 把你的 constant 加一个 variable 进去，就是讨论货车可能跟轿车啊。Okay, let's introduce one more coordinate before we jump into calculating some integral, actual integral. So let's do one more. Let's do cylindrical. Okay, so just now we fill our space using sphere, right? Okay, now we're going to fill our space using cylinder. Okay, so given a point, okay, find the cylinder that this point lives in. Okay, so how do we do that? How do we do that? Okay, so I'll give you a point. So find the cylinder that this point lives. Okay, so actually cylinder is easier than sphere. Okay, you just need to find a circle. Okay, where this point lives, and then you just extend the circle here. You don't need to rotate your circle. So what's the variable you need here? So in other words, you just need to know which circle this point lives in. So which circle you need to consider? You need to consider the xy plane that shifted up by z. Okay, and then look at which circle it's there in. Does that make sense? Does that make sense? wait. That makes sense. Some of you doesn't make sense. So let me draw here. Okay. Okay. So like this. So like this. So if I pick some point from the xy plane, okay, what do I do? Which circle, which cylinder does it lies in? So you just draw a circle around the origin. So the cylinder we consider here are all the cylinders. Do I use center here? But anyway, I can use center because I just care about infinite cylinders. Center at the origin. So what do I mean here? So you take a cylinder centered at the origin, okay, and then you expand the radius. Right, then you can fill out the whole space. Okay, does this make sense? Okay, so first let's take this point here on the xy plane. So how do you determine which cylinder it lives in? So what do? You do the same thing. What's the distance from this point to the origin? Okay, this is your radius, okay, or the row, right? And then take this row, form your circle, okay, and then form an infinite cylinder here. So you take infinitely many cylinders with different height. So let's say I got this cylinder here. Okay, let's form the cylinder. Okay. Okay, let's come back here. Okay, let's form our cylinder. Let's form a cylinder. Okay, and then like this, and like this. Okay. So how about the other point on this cylinder here? Let's say I pick this point. Okay, this is a valid point in R3. Okay, let's call the bottom one A, the top one B. How to find the cylinder for this B? How to find the cylinder for this B? what can you do? You actually can just project this B down to XY plane. Okay, project this B down to the XY plane, and then form the same radius of circle. And then you can see that they live on the same cylinder, but with a different height here. Okay, so what's the information you need here? Okay, so the information you need here is the angle, okay, you make on the circle, and then which radius of circle you take, and then just the height. Okay, just the height. Then this will determine all the point, okay, in R3, which cylinder they live in. Does it make sense or not? Does it make Okay. No? Okay. Okay. Okay, let's try an example here. Once you do example, maybe this concept will click in more. So let's find the rectangular coordinates for the point whose cylindrical coordinate is 2 pi over 3 and 1. Okay. So maybe let's just try and plot this rectangular coordinate, right? Let's plot it. Let's have an idea. Where's this point? So let's say we have these x, y, and z. So in the x direction, it is 2. Okay. 2 3. Where is 2 pi over 3? This is the angle from the positive x-axis. Going clockwise or anti-clockwise? Clockwise or anti-clockwise? In the convention of polar coordinate, is it anti-clockwise or clockwise? Anti. Okay, so it's anti. So going from 0 to 2 pi over 3. Where is 2 pi over 3? 2 pi over 3 is 60, 120. So it's on the second quadrant here, somewhere here, right? Okay, let's say this is 2 pi over 3. Okay, in the direction of in the length 2 vector here. Okay, with the height 1. Okay, with the height 1 here. So I just leave the 2 out here. Does that make sense? So the cylinder it lies is the cylinder with circle radius 2. This is the infinite cylinder it lies in. Okay, so in this case here, let's try and figure out what is the x, y, and z. Let's see, does this make sense to our picture? So x here, I haven't really tell you what is x. So really, we are doing polar coordinate here. So x here is just r cos theta, okay? And then y is just r sine theta. And then z will just remain as z. Okay. So r cos theta here is 2 cos 2 pi over 3. And then r sine theta here is r sine 2 pi over 3. And then z is just 1. So in this case here, what is 2 cos 2 pi over 3? Times negative half, which is negative 1. And then sine 2 pi over 3 is just square root 3 over 2. So 2 times square root 3 over 2, you get square root 3. So the coordinate is going from 2 pi over 3, 1 to negative 1, square root 3, and 1. Okay, which is on this octant, on the second octant. Okay, does that make sense? Negative x, right? Negative x in the second quadrant, and then it's a positive z, so going up. Okay, and this is the second octant in your R3. So you also count your octant from the positive top to positive bottom, anti-clockwise. Okay. Okay, no? Any question applying this cylindrical formula here? So from here again, let's look into more here. See here, what is going on here? Actually, really, you just have the polar coordinate here. Okay, with an extra height variable. That's all. Okay, so this is an extension from the R2, right? So how you build R2 from R3 from R2? How do you build R3 from R2? Here, yeah, you got a plane. How you build a box? Huh? You can turn it around, but for here you don't need. You just stack a lot of plane together. So I'm stacking a lot of circles together. Okay, no? So this is the idea of the cylinder. You stack a lot of circles together. Yeah. For spherical, you can turn the circle around, rotate the circle. Okay, no? Yeah, this is some action we can do to the circle. So circle become a very important subject in mathematics to study space. We study function from circles into space. Okay. And then this thing is what we call a homotopy. If you go further in algebraic topology, you will see this. We study functions from circle into spaces. Okay, yeah. So from calculus, you can see that we describe all the points using circles. Okay, how to describe points using cylinder, how to describe point using sphere. But sphere, cylinder, these are all made up by circle anyway. Okay, so circle become a very important subject. Object, not subject, object. Okay, in mathematics. Okay, let's continue. So how about the other direction? I give you a set of cylindrical coordinate whose rectangular coordinate is 3 minus 3 minus 7. Okay, so I think this is a bit trickier, right? Because we go the other way around. So what set of equation we can form here? We can form set of two equations. Right. So the first one is 3 equals to r cos theta. The other one is minus 3 equals to r sine theta. Z, there's not much you can play. Minus 7 equal to minus 7. Right. So how to do this? How to get something useful out of it? So you will take 2 divided by 1. Yes, 2 divided by 1. Something wrong with not. So you get tangent theta equals to minus 1. So when is it minus 1? When is it minus 1? When is it minus 1? When is tangent theta minus 1? 3 pi over 4 and pi over 4. Okay. Is it minus pi over 4? Let me think. 7 pi over 4. Yeah. Okay. Minus pi over 4 also works, right? Because you remember this tangent theta is a periodic function. Okay. Actually, there's infinitely many theta that equals to minus 1. But where's the domain of our theta? Remember, where's the domain of our theta? We just fix from 0 to 2 pi. Okay. Or we just throw 2 pi away because 0 will go back to 2 pi. Okay. So 0 to 2 pi would be enough to fill up my space. If I go more, that means I wrap around my space again and again. Okay. Okay. Yeah. All right. So let's throw these. So these are the two theta we could get. Okay. So which theta we should pick here then? Which theta we should pick here then? Yes, depend on our point here. Okay, where's this point here? Where's this point? So let's draw the picture again. Quadrant, just quadrant is enough to describe or not? Because R3 split into 8 or 10, right? So let's see where is it first. So here's 3, minus 3 is here, minus 7 is bottom, so it's going downward. Okay. This is the fourth quadrant, sure. Fourth quadrant, but fourth quadrant, remember in the octane is split into 2 parts again, right? Okay, so basically this is in the 1, 2, 3, 6, 7, 8, 8 octane. Okay, so we will count this octane as 1, 2, 3, and wait, 2 and 3 necessarily. 3 here, and then 4 at one side, and then count the bottom again. Can you imagine or not? So 1, 2, 3, 4 at the top, and then same order 5, 6, 7, 8. Does it make sense? How in the anti-clockwise sense? Okay.
As usual, but
Yes.
But the positive side.
Yes. Yes, correct. Yes, that's the way to understand it. Yes, that's the way to understand it. So in the R2 case, you count from the positive x-axis clockwise, right? But remember, you go into R3, meaning you extend the plane up and down. Okay, up and down. So when you do this, then the top part have 4 quadrant, the bottom part have 4 octane, not quadrant anymore, octane. Okay? Okay, no? Does it make sense? Make sense? Everyone know how this language, how is the language of octane? So I will say that minus 3, sorry, 3, minus 3, minus 7 lies in the 8 octane. So everyone can 8. One can imagine this 8 or 10. Can locate this octane or not in R3? Can or not? Can or not? Can count the octane? Anyone got problem counting octane? Got problem? You got problem? So what should we do? Hang on. Huh? You happy?
Yeah, I get it. So yeah, you can lie in that.
So how you explain the octane? So how to tell your friend? Ah, okay, that makes sense also. Yeah, you can imagine there's a 2 times 2, not 2 times 2, 2 times 2, 2 times 2, Rubik cube. 2 times 2 Rubik cube. So there are 8 pieces, right? Yeah. So you count from the positive x-axis going anti-clockwise, 1, 2, 3, 4, and then start again from the bottom 4. Okay? Make sense? Okay. So this is in the last one. So this point is in the last one. So since it lies in the 8 or 10 rank, what's the theta? Theta must be in the 4th quadrant. So which theta is in the 4th quadrant? 3 pi of 4 is what? 15 times 3. Correct or not? Wait, sorry. Divide wrong. 180 divided 4. 4, 4, 16. 16, 55, 45. 45 times 3 is 135. 135, which quadrant? Huh? 2nd quadrant, right? But we need the 4th quadrant because it's the 8 or 10. So it is 7 pi over 4. 7 pi over 4 is 300, yeah, 315, correct. So this is a 315 degree. Okay. Okay, so I write degree so that, I mean, I'm familiar with 360. I'm not sure about you. Maybe you can imagine pi. Okay, so let's get our, what else we need to compute? R. Okay, we need to compute our R. What's our R then? Okay, so sum it in. So we get 3 pi equals to R sine 7 pi over 4. So this implies that my R is equals to 3 square root 2. So you get 6 square root over square root 2, which is 3 square root 2. Okay. Because sine of 7 pi over 2 is what? This is equals to negative square root 2 over 2. Okay. So 3 minus 3 minus 7 will be get changed to 3 square root 2, 7 pi over 4, and then minus 7. Okay? Okay, Anna? Yeah. Okay, these are just changing variable. So later on we'll do integral. So when we do this change of variable, right, you should imagine this changing in your point. Okay. What's the most important thing to take away here is you need to know what variable we use to describe spherical, what variable we use to describe sphere. Okay, what kind of variable we use in each case. Okay. Okay, let's come back and do some exercises. Let's see. Should we go to this first? Let me think. How about we talk a bit more on integration first, and then we go. Okay, so how about in cylindrical? So how do you do triple integral here? So what is the cylinder rectangle looks like, or boxes look like? So it looks something like this. So you should imagine you have the polar rectangle, right? We have polar rectangle that increase in height now. Okay, so it's like a polar cuboid, maybe, yeah, polar cuboid, yeah. So you imagine this is a real pizza now, all right? Before just a slice, it's like an Italian pizza, but now it's a it's a pizza pizza. So thick, okay, too thick now, okay. It's going thick, okay, yeah, yeah, okay, yeah. Become a thick crust. Okay, now you look at the thick crust now. Okay, one thing to note here. Okay, in the cylindrical coordinate, similar to the polar coordinate. Okay, you have an extra R. Okay, extra R contribution here, extra R factor here. How does extra R pops up? Remember last time what I said? You have a rectangle, but your rectangle gets stretched a little bit. Okay. Soon you will see how this come out formally. I'm not sure will be done today or not. Maybe not today. Maybe next lecture you'll see. Okay, so this is the cylindrical rectangle. Okay, you consider when you cylindrical. So similar to the 2D case, you could imagine a box, right? You start with a rectangular box. So what's a cylindrical rectangle? You try and deform it a little bit. Okay, try and deform it a little bit. Okay. As how you deform the rectangle. How about cylindrical? Where is cylindrical? Let me jump to the cylindrical one. Okay, how about cylindrical? Okay, so this is the cylindrical. Sorry, how about the spherical coordinate? So this is the spherical rectangle you could get. So it's like a I'll say this thing is like a sector of the ball. Okay, you should imagine this as a sector of a ball here. Okay. Just now we stretch in which way? Let me see. So just now we stretch in this way, okay, horizontally, but this one we stretch in the radial direction. Okay, we stretch the box in the radial direction. Does it make sense? So you have a rectangular box, but you stretch in a radial direction. Okay, see where it gets stretched here. You get stretched here. Okay, you stretch in a radial direction. Okay, since the box gets stretched again, this means there's another factor popping up. Okay, but the factor here is rho square sine phi. Okay, not just rho, but rho square sine phi. Depend on phi. Okay, depend on phi. Not just radius. It depends on phi as well. Okay. Okay. This is okay. Let's try and do some exercises. Let's see. Okay, how about we keep doing these first, and then maybe next time we jump to the last example. Okay, let's try this exercise. Try this one. Okay, try and evaluate this looks complicated exponential function. Okay. Over a domain. This domain is a ball. It's a unique ball. Okay, x squared plus y squared plus z squared less than or equal to 1. Okay, so this is a ball. So which coordinate is useful? Spherical, cylindrical, or xy? Spherical, okay, because spherical will give you exactly the ball. Okay, so how do you describe this ball using spherical coordinate? So what do you need for spherical? You need radius, right? Okay, you need the angle from the positive x-axis, which is called the theta. Okay, and then angle from the positive z-axis, phi. Okay, so how to form this ball here? So you see, you have 3 variables first. You need to use another 3 variable to describe it. Why? Because R3 is 3-dimensional. 3-dimensional, you need 3 bases. Okay. Okay, so rho, what's your radius of your ball? 0 to 1. Okay. How about theta? What's the theta you should take? 0 to 2 pi. So you swipe out this. Okay, you swipe out this. Now you want the ball. So you need a slice of a watermelon. So you need to go from 0 to pi. Okay. All right. So your triple integral here just transform to a spherical rectangle. So you become d rho, d theta, and d phi. So phi is going from 0 to pi, theta going from 0 to 2 pi, rho going from 0 to 1. Okay, how about your x squared plus y squared plus z squared here? Becomes what? Become rho squared. So you see, that's why they put this question as x squared plus y squared plus z squared. It looks complicated, but under the change of variable, it just becomes a rho squared. And then why put 3 over 2 here? You can see that there's a power of 2 inside. Then they will cancel. And because we change our variable from x, y, z, right? So we need to have an extra factor. So the factor for spherical coordinate is rho squared sine phi. That's all. So this becomes what? So e to the rho to the cube, rho square sine phi. Okay? Yeah. Mm. 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 Look familiar or not? Does this look familiar? A little? The sad face and the happy face. Isn't it this the sad face and the happy face? Right. Isn't it? The sad face, happy face. This is the happy face, right? You can do integration by substitution. Okay. See, from here, what can you see? I have a variable in terms of rho, theta, and phi. But you can see that all these functions that contain rho or phi are product of function. So we can evaluate this iterated integral as a product of integral. Okay. We can evaluate this iterated integral as a product of integral. I have this extra 1/3. Something wrong, is it? Okay, nothing wrong. It's because I introduced the 3 inside. You will see why I do this. Okay. One thing to note here. Please remember, this is iterated integral. This is not the product of integral, but this is the result of a theorem. Okay, this is the result of theorem or proposition. Okay, does it make sense or not? Iterated integral you need to do in order. You need to integrate inside and then slowly open up the integral. But this is a product of integral. It's really different thing. Okay, so how to integrate this? So first you will get minus cos phi from 0 to pi, and then this one immediately you get 2 pi. And why I do this? Why do I do this? Because if you let u equals to rho cube, du is 3 rho square. Okay. So can I immediately do it? Can I immediately do the integral? Can you guys follow this integral? Cannot. Okay. So let's do it slowly here. So let u equals to rho cube, right? So du equals to 3 rho squared 0, right? So the integral becomes what? No need to care about the integration domain first. Let's do this e to the rho cube 0. So this integral here becomes a du e to the u. Integrate eu, you just get u. Okay, so you just get e to the rho cube. So the extra factor here, remember to keep it in. Continue, just continue. So 1 plus 1 times 2 pi times 1/3 e minus 1, which is 4/3 e minus 1 pi. Okay? Okay or not? Okay. So next time, we will repeat some exercise for general region, and then we will continue integration in cylindrical and spherical. Okay or not? Okay, any question before we break for next week? Next week Monday is a holiday, right? Hey, when's your next assignment due? I forgot. After presentation. Before presentation? Seriously? Next Wednesday. Before presentation. I let you try first. Next week we can discuss again. Still got Tuesday, right? Yeah, I let you work hard first. Work hard first this weekend. Okay. Maybe the assignment will give you some hint what to do in the presentation. Hey, if someone can talk about open and close in real life, I will be very surprised. Yeah. Okay, actually I got one very interesting video. If you can do about open set and close set, talk about it. It is about physics also. Yeah, I believe the teacher come. Wait. Quick. Okay, let me see.
You can have a open particle type one.
This one.
Lands on this whole situation of quantum gravity and particle wave duality. Close that exists in our world of
Yes, this
particle
one.
wave duality.
So if someone can talk about this, it would be nice. Open refer to a wave, close refer to a particle, and then they are close and open set, which refer to the particle wave duality. I can use open set and closed set to describe physical state in this world. Okay, if someone can do this, will be good. Okay. A set. So for the exam, right, you need to prepare what is a closed set, what is the open set, what is the set that can be both closed and open. Okay. And then not closed and not open. All possibility, you can find this kind of set. And this is exhibited by physics in this world, as what he said. You can try and go to search this video here, a topological approach to quantum gravity.
With
Okay.
do through quantum.
Okay.
There.
If someone want to pick up this, would be nice. Okay, see you next week. See you next week.
A ring is a group like the real numbers that has the following key properties. There's two operators, like condition and